Hi, Assalamualaikum and hello everyone. Welcome to our video presentation for assignment 2 of the course assignment 3043. Before we start, I would like to introduce you my group members, which is Siti Aisyah binti Napi, Raja Zarina, Wan Nur Atira, Aiman Afifi, and Alif Ashraf. In this video, we will be presenting two real-world scenarios that involve 1. A second-order linear homogeneous differential equation, and 2. A second-order linear non-homogeneous differential equation. Let's briefly explain what each of these equations involves, using simple examples so you can imagine the situation easily. For homogeneous equation, which is no external force, let's imagine this. You're holding a spring with a small weight at the end. You pull it down, then let go. What happens? The spring starts to bounce up and down on its own without anyone touching it again. That's what we call a homogeneous system. The movement comes only from the system itself, and there is no outside force acting on it. The general form of the equation is ay double prime plus by prime plus cy equal to 0. Yes, there's really nothing after the equal sign. That means the system is self-driven and we're only looking at its natural behavior. And I am going to show you simple steps to solve. First, start by writing the equation based on the scenario. Second, turn it into a characteristic equation, which is ar squared plus br plus c equal to 0. Third, use the roots to write the general solution, which could involve exponential functions, sine, cosines, or both depending on the roots. This type of equation is used for systems like a free vibrating spring or a pendulum swinging without wind or a resistance. Second, non-homogeneous equation with external force. Now imagine something more dynamic. You're in a car and you drive over a speed bump. The car moves up and down, but not because it wants to, it's reacting to the road bump. This is a perfect example of a non-homogeneous system, which is something is happening because of an external force. That force is what makes it non-homogeneous. The general form of the equation is ay double prime plus by prime plus cy equal to fx. Here, fx is the external force, like the bump or pothole on the road. Steps to solve. First, solve the homogeneous part as before to get the complementary solution. Next, find a particular solution that fits the external force. And third, combine both to get the full answer, which is y equal to y homogeneous plus y particular. In this case of a vehicle suspension, the system includes spring, which compress and extend, dampers or shock absorbers, which reduce bouncing, and of course, the bump as the forcing function fx. So, the suspension system equation models how your car reacts to the road, keeping your ride smooth. So throughout this video, we'll guide you through both types of equations using real-life scenarios, simple math steps, and clear diagrams to help make it all easy to understand. Let's get started with our first scenario.
Next, for the second order linear homogeneous, for the real world scenarios, as example, a mass spring system is considered, where a mass of 1 kilogram is attached to a spring with a spring constant of 9 Newton meter. The mass is initially displayed 0.7 meter from its equilibrium position and released with an initially velocity of 1 meter second. The system is assumed to be undamped meaning there is no frictional force. Okay, for the question, determine the position of the mass as a function of time, xt. Solution. Firstly, formulate the differential equation. The equation of motion for an undamped mass spring system is given by md square x over dt square plus kx equals to 0, where m is the mass, k is the spring constant, and x is the displacement from the equilibrium position. So substituting the given value, m equals to 1 kilogram and k is 9 Newton meter, the equation becomes d square x over dt square plus 9x equals to 0. So this is a second order linear homogeneous differential equation. Next, solve the characteristic equation. The characteristic equation for this differential equation is arc square plus 9 equals to 0. Solving for arc give arc equals to plus minus negative 9 equals to plus minus 3i, where I is the imaginary unit.
After we solving for r, we get r equal to plus minus 3i, which is I is the imaginary unit. So for the next solution, since the roots are imaginary, the general solution is of the form xt equal to a cos 3t plus b sine 3t, where a and b are constants determined by the initial conditions. So for the next solution, solution 4, we apply initial conditions. We have two initial conditions. The first is initial displacements. We denote as x0. We get 0.7 meter. For the second condition is initial velocity. We denote as x prime 0 equal to 1 meter per second. Then we apply the initial displacement with the general solution. We get x0 for initial displacement equal to a cos 0 plus b sine 0. We get a because b sine 0 is 0. So a cos 0 plus 0, we get a. So a is 0.7. Okay, because x0 is 0.7. Then apply the initial velocity, which is first derivative of xt. So x prime t equal to negative 3 is sine 3t plus 3b cos 3t. So we substitute t with the 0. Okay. So x prime 0 equal to negative 3a sine 0 plus 3b cos 0. So x prime 0 we get 1 equal to 3b. So b we get 1 over 3. Next, for the final solution, we substituting the values of a and b into the general solution. We get the specific solution for the position of the mass as a function of time. We get xt equal to 0.7 cos 3t plus 1 over 3 sine 3t. So this for the example of scenario for the linear homogeneous equation.
Okay, hi everyone. My name is Raja Zarina. So before I start to explain how to solve a second order linear non-homogeneous differential equation, I would like to ask you a question. Okay? Okay, the question is, when you are in the car, have you ever felt your car bouncing slightly after driving over a bump? Hmm? Okay, well, that's your suspension system in action. So, today we are going to explore how this real life situation can be modeled using a second order linear non homogeneous differential equation. Okay, first, let's read the question first. Vehicle suspension system. Imagine you're modeling the vertical motion of a car suspension system as it drives over a bumpy road. The car has a suspension spring constant K equal to 5 meter per meter, a damping coefficient C equal to 2 Newton second per meter, and the mass of the system representing the wheel and part of the chassis is 1 kilogram. The road causes a periodic forcing function due to uneven surface modeled by F naught cos omega t, where F naught equal to 3 Newton and omega equal to 2 radian per second. So let's go to the next part. Okay, from the previous slide, we got that M equal to 1 kg is the mass, C equal to 2 Newton second per meter is the damping coefficient, K equal to 5 Newton per meter is the spring constant, F naught equal to 3 Newton is the amplitude of the external force, omega equal to 2 radian per second, and our displacement denoted by YT. Okay, next. Alright, now let's build our differential equation based on that system. We are using the standard form, which is my double prime plus cy prime plus ky equal to f naught cos omega t. And then we substitute our values together, we will get y double prime plus 2y prime plus 5y equal to 3 cos 2t. As you can see, this equation is non-homogeneous equation because the right hand side is not 0. Okay, to solve second order linear non-homogeneous differential equation, our first step is to find the general solution, which is y equal to y homogeneous plus y particular. That means we have to solve the homogeneous part first. So our homogeneous equation is y double prime plus 2y prime plus 5y equal to 0. And then we have to create characteristic equation where it should be r squared plus 2r plus 5 equal to 0. Next, let's solve that equation using quadratic formula. If you not remember the quadratic formula, I already attached the formula at the bottom of the slide. If you got complex roots, you are on the right path because this equation we should get r equal to negative 1 plus minus 2i, where I is imaginary unit, which is give us the solution for homogeneous is e to the power of negative t times c1 cos 2t plus c2 sin 2t. That's all from me.
Next, for the step 2, we solve for the particular solution, which is from the homogeneous solution, we got yp equal to a cos 2t plus b sin 2t. And then we find the derivative, which is the first derivative is negative 2a sin 2t plus 2b cos 2t, and the second derivative is negative 4a cos 2t minus 4b sin 2t. And then we substitute the derivative into the original solution, which is y double prime plus 2y prime plus 5y equal to 3 cos 2t. And then we got negative 4a cos 2t minus 4b sin 2t plus 2 multiplied by negative 2a sin 2t plus 2b cos 2t. Substitute by 5 multiplied by negative 2a sin 2t plus 2b cos 2t equal to 3 cos 2t. From the substitution, we got the coefficient of cos 2t and sin 2t, which is cos 2t is equal to a plus 4b and sin 2t is equal to b minus 4a. And then we compare the coefficient of cos 2t and sin 2t equal to 3 cos 2t, and we got a plus 4b equal to 3 for the equation 1 and b equal to 4a, which is equation 2. After that, we substitute the equation 2 into equation 1, and then we got a is equal to 3 over 17. Then we substitute a into equation 2, and then we got b equal to 12 over 17. So the particular solution is yp equal to 3 over 70 cos 2t plus 12 over 70 sin 2t. And then we solve for the step 3, which is solve for general solution. We substitute into the formula, which is y equal to yn plus yp, which is we got yn from the homogeneous solution in step 1. And then we get e power of negative t multiplied by c1 cos 2t plus c2 sin 2t plus 3 over 70 cos 2t and 12 over 17 sin 2t. Therefore, the general solution is yt equal to e power of negative t multiply by C1 cos 2t plus C2 sin 2t multiply by 3 over 70 cos 2t plus 12 over 70 sin 2t.
And that's a wrap, everyone. Today we explored two real-life scenarios involving second-order differential equations, one where things move on their own and one where they get a little push from outside. We learned how a spring bounces freely, which is homogeneous, and how a car reacts to a bump, which is non-homogeneous. From springs to suspensions, math really is everywhere. So thanks for watching. Bye bye. Assalamualaikum.